All right. Okay, let's get into it. So I'm Roshan, and I'm a researcher working for Marlin, working on a project called Kalypso, which is basically a proof market. Uh, More importantly, I'm here to talk more about the Aztec Provernet that just happened and how we are integrating the Aztec Provernet with Kalypso. So the talk is going to follow with this basic structure. We'll start with an explanation of like Kalypso's architecture and how all of that works. We'll then go into Aztec's architecture, more specifically on the proving side. We'll talk a bit about how we made the integration and how we are sort of like envisioning things. We'll also touch upon a couple of like open questions and like paper cuts that we found during the integration, and I'd have a little surprise for you guys at the end. Okay, so Kalypso is a confidential proof market, right? So what that means is it's a marketplace, an order book-based marketplace. And on one side, you have specialized hardware operators placing like asks, who are basically saying, hey, I'm ready to generate proofs for specific proof systems for, let's say, this price and this time or whatever, right? On the demand side, you have various applications, for example, like rollups, bridges, oracles, etc., which like require ZK proofs, and they form the buy side of the order book. So they are basically placing orders saying, hey, I need a proof generated for my block, and like what time and price can you do it for, right? In the middle of all that, there's a matching engine, which is basically doing the matching of like asks and bids on the order book, and yeah. So the reason why this is important is because it's not that optimal for applications to sort of be running their own specialized hardware themselves, because there's a lot of efficiency that you can unlock just by having more utilization and just by having like better hardware that's actually out there. For example, stuff like GPUs, SX, and all that, which projects themselves might not want to run, right? So Kalypso looks something like this. So it's sort of structured similar to a compiler. So you basically have like front-end and back-end phases, and it's all mediated in the middle by a taskbook, which is probably like analogous to like an IR, right? So on the front end, you basically have a lot of like markets. Each market has its own order book with like buy and sell sides. All of these order books are essentially run by a matching engine that's run on Oyster, which does the matching. And on the demand side, again, you have all the applications which feed in orders to the order book. The matching engine does the matching and puts that into the task book, right? So once you have an order in the task book, it's then up to the provers to actually do the ZK proof generation. And you can have like multiple provers with like specialized hardware if needed, GPUs, SXTs, and so on, right? And Kalypso is, of course, open. And what that means is that anyone can create a market and customize parameters. It's permissionless, decentralized. You can like set various parameters in this thing, starting with like minimum stake. So all the generators in the marketplace stake certain amounts and place guarantees on like when they would be able to generate a proof. So you can set a stake amount. You can set your slashing rates. Maybe you don't want to slash all of a generator's money, just a little bit. So you can set all that. And you can also set your deadlines and jobs. So you can say, hey, I'm a roll-up. My block time is, let's say, 10 minutes or something. So I want my proofs to be generated within 10 minutes, and the market will basically enforce that for you, right? So that's Kalypso. Let's move on to Aztec. Aztec is basically built as a privacy-first ZK rollup. That's a direct code. And what that essentially translates to is that there are like two sides to every transaction, right? So there's a private side and then there's a public side. On the private side, the users basically generate proofs for using their private data on their own devices, and they send that proof to the sequencer. Now, the sequencer essentially does the public side. It is more or less like a smart contract. You basically get to run some public code in your transaction. Important thing to note here is that the sequencers don't really do any proving, right? So the sequencers run what's called as a prover auction. So they basically say, here, I have a block or an epoch these days, and give me bids on like who can generate a proof for this, like faster, cheaper, etc. Right? The whole prover architecture started off from a forum post asking for like proposals on like how to design a prover network, and it all ended up with this, which is something called like Fernet. It's more commonly referred to as Provernet these days. But the basic idea is this. Your proving is sort of like divided into multiple phases, right? On the proposal side, you basically have a block proposer making a proposal, right? At the end of that, you have a small prover auction that's basically asking provers to bid on who wants to actually generate a proof for a block. And the winner basically gets to do a proving stage where they actually generate a proof, and then there's a finalization, right? So there's this pipeline that's happening for basically every block or like every epoch that Aztec is generating. There are some important like characteristics of this proving that are important to mention. The first one is that it's all pipeline. So all of these stages in Aztec basically overlap with each other. You don't really wait for proving in order to make a new proposal for the next block, right? And it's actually quite similar to how like a modern CPU works today. Everything is like sort of nice pipelined. The implications of this is that much like a normal CPU, you have the concept of like CPU stalls, which is it's quite possible that some prover actually accepts a proving job and doesn't actually do the job, right? So in that case, you basically end up having to throw away a lot of work. And there are two important parameters over here. Lower proving time is really important because that basically reduces the length of like each stage. And the other thing that's important is like high reliability, because proving time basically determines how much work you have to throw away per instance of like any error happening, and reliability determines how many instances of like errors actually happen, right? The second important part is that proofs on Aztec aren't really that simple. A single block proof for Aztec looks something like this. It probably has something around like 20 proofs or so for like a small block of like 2 to 4 transactions. The work is basically batched, right, into epochs of like multiple blocks, and each block goes through something like this, right? So there's a lot of steps, but there's also a lot of dependencies between the steps. So the outputs of like certain steps basically feed into inputs of other steps and so on until you get one single proof at the end, right? The hard part about all this is that this tree basically depends on the number of transactions that are in there. The more transactions you have, a bigger tree you have with like more levels. Even within a transaction, you might have different number of like public and private interactions. So your tree might be bigger or smaller even at the leaves based on like how many transactions and like what they do, right? So end of the day, all of this just results in like a lot of variance in terms of what a prover is expected to do, right? So to summarize what we have, Kalypso is like almost entirely order book based right now, and each job is independent. It's just fire and forget. Each market is expected to have a fixed shape because that helps provers actually place bids on how much time it's going to take and like what price they want to charge, right? And the advantage of Kalypso is, of course, that it provides like fast and like really optimized proving, right? And just the structure of the order book means that it's massively parallel because you have a lot of people just placing bids on the other side, right? Now, Aztec, on the other hand, is auction-based, not order books. And there are a lot of steps, as we just saw on the previous slide, right? And there's a lot of like interdependence between the steps as well. And all of this basically means that there's a lot of like high variance, which doesn't sit quite well with Kalypso, which wants like a fixed shape and stuff like that, right? So, okay. Given these two, there's a lot of things that there's a bit of like impedance mismatch between Kalypso and Aztec based on like what they want. So let's look at how we actually did the integration, right? So to start with, one decision that we made was this, which is creating one market per proof size, right? So all of the boxes and circles that you see over here today on Kalypso basically represent like individual markets, more or less, right? The main advantage, of course, is that each of those boxes is like a single proof, and each proof type is basically like a fixed size, right? So it maps really well onto like a market structure. And of course, markets are like inherently parallel because there's a lot of provers on one side, which means that you basically get to parallelize your entire tree over here, like at least as much as you can, right? And of course, markets also give you competitive pricing because provers are competing against each other. And it also lets provers specialize in like certain aspects of proofs. For example, maybe one of the boxes is like really good with the GPU. One of the other boxes might be really good with a smaller computer that's like way cheaper, right? So Kalypso basically lets you do all of this for Aztec. The other big decision is that we chose to go with a common compute pool across all this. And it's basically it's shared across all of the boxes that you see over here, right? The matching engine basically ensures that even though you might have provers listed in a lot of markets, of course, in reality, provers have a fixed capacity, and the matching engine ensures that you don't really go above that, right? The main advantage of this is that you now basically get automatic rebalancing between markets, right? So, for example, let's say some blocks have a lot of transactions, but they don't really have a lot of public transfers, right? So, your proving capacity in the marketplace basically gets to rebalance between each of these boxes based on like the number of boxes that are in a given block, right? The nice part about this is that it's not just Aztec, but the rebalancing happens across the space, which means maybe there's airdrop on Aztec someday and there's a lot of demand for transactions, right? We can easily pull compute capacity from like other rollups, like latent capacity, and add that to Aztec, right? The last kind of iffy decision is the need for an off-protocol coordinator. So there is still a bit of like impedance mismatch between Kalypso and Aztec, so we need somebody to actually resolve it, and that's the job of the coordinator. So the coordinator places bets on Aztec saying, hey, I take responsibility for ensuring that you get proofs on time, and the coordinator in turn goes and places jobs in the marketplace and say, hey, help me actually get the proofs on time, right? So the job is basically to mediate between like auctions and order books and sort of resolve the impedance mismatch. It also has to place bonds on the Aztec side because Aztec has sticking slashing mechanisms. And on the Kalypso side, it also has to handle like failure recovery. For example, it's possible that certain provers fail, and it basically has to handle that and maybe place new jobs, maybe place the same job multiple times in order to ensure reliability and all that, right? All that is the job of the protocol coordinator. So in the course of all this, we basically found two main things that we think could be better. The first obvious one is, of course, the coordinator, because it's not that great to have like off-protocol actors. So the open question is, of course, can you make a reliable but like a decentralized coordination system that can sort of like handle placing jobs on Kalypso, failure recovery, and like package all that up into like a simple auction mechanism, right? The important thing is to do that while still retaining the benefits of order books, which is that you get price discovery, you just get to see what orders are there on the order book, right? And it's of course competitive, and it lets provers specialize in different markets. Provers can say, hey, I'm only good at making proofs for these specific proof systems, right? You can do stuff like that. The other major question is the capital efficiency, because Kalypso also has a staking mechanism like Aztec. It basically gives you guarantees on the prover actually making the proof within time, right? So this leads to, of course, capital inefficiency, because now there's stake locked up in two different protocols for basically the same proof. So can you sort of reuse stake between Kalypso and Aztec, and like what would that actually look like, right? So before I end, okay, here's a Easter egg for you guys. Something a little surprising that we've seen happen over the course of the integration is the ability to sort of monetize the expertise of the ZK people out here, right? The Kalypso marketplace basically ensures that's a good incentive alignment between the provers and the ZK experts and engineers over here. Because it's a competitive marketplace, provers that are more optimized and can do proofs like faster and cheaper basically get more jobs and revenue, right? Another important aspect is that provers can be entirely proprietary, which means you can just write code, optimize code, run a prover without having to actually show that to anyone. You could also license code if you don't want to do the hardware side. You can write optimized code, talk with other provers, license the code to them, and do all that. Or you can even do like consulting gigs. For example, you can tell provers, hey, I'm willing to optimize this particular market for you, and you can get gigs that way, right? And that brings me to the end. Thank you guys for listening. Any questions?
Hi. So you mentioned that you use an order book system to match provers with people who want stuff to be proved. So, and you do address variance in how long it takes to prove something.
Yeah.
Right. So, So that kind of means that the prover needs to know beforehand how long. One market is a market is a specific computation, right?
Ideally, yes. It's usually a specific proof system and a specific circuit together, right?
Right.
So essentially, provers on the market basically get to know, hey, the market is for this circuit, and they basically get to benchmark beforehand and see, hey, I can do it this fast, I can do it this cheap, and so on, and then they can place bids on the marketplace.
Right. So, is there any responsibility from the buyer to not artificially construct a difficult problem to just mess with the prover?
Not really right now. The main reason is because a lot of markets that exist on Kalypso are more or less constant time markets, right? So a lot of stuff is like focused on snarks, more or less, which means they are just inherently constant time, right? So for one, that helps. Even in the case of we've onboarded a few stock markets as well, but turns out in stocks you can basically just round things up to a power of 2 and just create individual markets that way, right? So even for stocks, it's not that hard to get like a fixed size outcome out of it, even though like stocks are supposed to be non-fixed size, right?
Okay, thanks.
Thank you. I think it's super helpful because it's a very fresh topic. So I have one question. Yeah. So do you think people who are going to run the sequencer will also be interested to run the prover, and then it will end up with sequencer prover consolidation?
It's possible for sure, but at least what we're seeing in the space is there doesn't seem to be that much of an interest from sequencers, especially because proving is like really intensive. So the Aztec Provernet that's about to happen, the estimate is that you'll need about 1,000 prover nodes to like prove a single epoch, right? That's the hardware level that you need. And I'm not sure if sequencers are really up to running like 1,000 nodes. 10, 20 maybe, but 1,000 is like a lot, right?
Thank you. Thank you, Roshan.